B3. So it does all these different structures. That's why you hear nicotinamide, nicotine, amide. Get it? He's smoking ribo ADP. This is part, like up here with ruby, it's part of a longer molecule, a ribose and an ADP. Well, that's kind of what was up here, right? For the same structure with ribose holding on to ruby there. Down here, you're going to have the NAD with a ribose, ADP, that's an adenine diphosphate, which is almost exactly what the flavin was up there. Diphosphates, 2 phosphorus, there's the adenine, and instead of being bound to the nicotinamide, single ring structure, it's bound to your B2. So see, by playing with the cartoons on this, you can compare things a lot easier, I think. ADP with ruby, and see again, it's got the adenine up top there. This is one I get confused because it's a misnomer. They call it like flavin mononucleotide, but it's not a FD. They call it dinucleotide, but there's only one nucleotide, the A. So I see I'm confusing myself. So if you're confused, you're right on track. So again, here is the other one from nicotinamide, NAD plus. Plus is on the nitrogen because it's doing 4 bonds here. It's got a double bound to a carbon, single bound, that's 3, and then the 4th goes to the ribo, which is a 5-membered sugar ring like ruby, and ruby's holding on to an ADP, adenosine diphosphate. So somewhere in there is smoking a NAD cigar, smoking an ADP ribo cigar. I think the way it should be is it going to give me an arrow. I think the way it should be is that should be down there, and that should be up. That should be up there. That should be down. The way it should be, but we're not concerned because this is not going to be saved this way. So up here, let's show water. Everybody loves water, right? Well, water, I found, looks exactly like Mickey Mouse. And Mickey's got 2 proton ears. He's got electron pair hands. Water's H2O. 2 H's are the hydrogens. Electron pair, it does this thing called the octet. So you need 8 electrons. So 2 are always bonded whenever you have a bond to another element or atom. So 2 electrons holding that proton, 2 electrons holding that proton. 2, 4, here's a lone pair, 5, 6, his hands, 7, 8. Now, this is really what water looks like because they're grabby. Just like a magnet, kids. When you played with magnets, this is what water is. How does water stick to each other? Negatives are going to grab onto the ear of another water. Now, water you'll hear as being a universal solvent because of that lone pair of electrons. It's what's called dipolar. It means it's a magnet all by itself. It's got a plus side, a minus side. So it's a magnet, and the negatives can actually pull protons, or say sodium chloride up here we use for an example, salt. Salt dissolves. Salt water is a sodium plus, which means it didn't keep the electron, because chlorine kept the electron. So chlorine is a negative ion. We'll show you that more in detail later. Sodium is a plus ion. So a good question that I like to ask is, does water conduct electricity? Well, no, because you need these salts in there to do that. So water, I won't go into too much detail because I have a whole 45-minute lecture just on water. But the whole idea of acid-base chemistry is that water, when it pulls a proton off another water, becomes an acid. This is kind of the equivalent of our ammonia alien. That being a lone pair, like the alien, we'll do a mind meld, negative charge pulling a positive off. So this is the equivalent, they call it H3O+, but it should be H2OP+. That's the equivalent of the ammonium, NH4+. I know it's complicated, it's the first time you've heard it, but see, you really got a hold on me. OH, of course, ion, a negative attitude. Mickey took my proton here. So this is Mimi. Mimi gets a negative attitude when she lost her proton because the electron stayed. So that's OH minus, they call it. So this is a hydroxide anion. Anion means negative. This is the hydronium cation. Cations are positive. What are cations afraid of? Dog ions. What do cations like? Mouse ions. Okay, so that's a whole little proton game that you can play with water. Next, let's do a little bit more on our vitamin thing. We're going to have a lot of vitamins in this book here. Melatonin. This is the sleep molecule, and you'll be able to compare this. There's a cool little thing that goes from dopamine. Remember we had their dopamine down there with the El Capitan, the capsaicin, L-Dopa. L-Dopa will go, there's dopamine, there's serotonin, and then to melatonin. So all four of those molecules are similarly related. There's enzymes that make them different. So melatonin is the sleep molecule, you'll hear it. So here there's Ben, the aromatic ring again, says, oh, I'm sleepy. So this way you remember melatonin is for sleep. Up here, I used to have this drawn different. It's a whole different animal, but then I found I was drawing it wrong, so I had to change it. Now it's the tryptophan penguin. Can you see that there? Does it kind of look like a penguin? This is the backbone of your proteins, the amino acids. CO, here's the carboxylate acid, carboxylic acid, drawing of it, OH with the double bonded O. I like it better when it's the tail on the fish, like I had the proton gone, the negative share between the two oxygens. Here's a nitrogen, a carbon, carboxylate. So that's the backbone of the amino acid. There's a carbon, there's usually always a carbon hanging off there. And then the side chain, in this case, makes it tryptophan. So does it kind of look like a penguin? Kind of. So it's an aromatic ring. Nitrogen, see the triangle with one H on there. There's a lone pair of electrons in there somewhere too. So it could be drawn as an alien if you want to play other games. And when you get this too, what you'll see is all around the book here, I put an amino acid chain going all the way around. So here's the aspartic acid hanging off a carbon. So carbon to double bound O, to a nitrogen, to a carbon diamond, to a carbon diamond with a proline hanging off. Now we go to the way we draw this with using suits from the cards. So you can play a card game where you deal out the cards and you could only play what would go as the next atom in a protein or an amino acid. So it doesn't matter what the number is, but if you have a heart gets the 2 bonds off the diamonds. Diamonds have 4 bonds, so when you lay a diamond, you could lay a heart on it, you could lay another diamond, and then when you get the next diamond, you could lay a diamond, or a club, because the club represents the 3 bonds of a nitrogen. And then when you get a spade is what the hydrogen is. So hydrogen is a single bond. Carbon will do a bond off of anything, really. Carbon will bond to everything here. Carbon to an oxygen, carbon to a hydrogen spade, carbon to a club nitrogen. So look how, we'll just run this across here real slow and see the way there's lysine, and now the next amino acid will be on the opposite side, aspartic acid again. You got all diamond, oxygen, diamond to spade, diamond to hydrogen, diamond to a heart again, diamond, nitrogen, carbon, oxygen, carbon, nitrogen, carbon, oxygen, carbon, hydrogen, nitrogen, carbon. So see that? Using all the suits from the playing cards, you can string along an amino acid side chain. Threonine side chain. You got leucine, you got tryptophan, that should probably be on the opposite side there. Okay. Now again, the power of the cartoons here, I want to get in doing reactions when you can show what's happening to the molecules as different enzymes are working on them. Now breaking down glucose is a great example because what you end up getting is, end up way over there, pyruvate and then lactate. So you get lactic acid, lactate. So here you can have lactate represented as a weightlifter. So the negative charge is shared between those two oxygens. 1 and 2, there's only 3 carbons. So lactate with 3 carbons, an OH, carboxylic acid side chain, right? Well, then you would have, after an enzymatic reaction, here's Rudolph the red-nosed lactate. See, different ways of drawing it. Here's a methane, a carbon with 3 hydrogens bound to another carbon, carbon with the carboxylic acid. Compare that to the pyruvate tiger and see if you can see what the enzyme did to change. Pyruvate came in, this is in your mitochondria now, it gets the pyruvate in. The first reaction it does is it changes pyruvate to lactate. You got an OH. I don't see an OH there. Well, here's an OH. Okay, so you got an OH and OH, double bound O. That's the carboxylic acid because you can write it. Remember I said I prefer this way, but I drew this just so I could make a tiger out of it. So this is actually that, the double bond part. I'm pointing at the wrong part here. Pointing at the muscle man, but here we'll do Rudolph here. The tail is this part. So we've got that the same. That goes to a carbon, to a ketone. Look at there, a double bound O. We come over here, what's it got? Not a double bound O. It's got a methyl up there, a methyl up there. So that's the same. That tail's the same. So right there, that's the reaction that got worked on. Pyruvate came in, the first reaction was it got rid of that O. So what's fun when you're doing the reactions, what you'll see is this being real electronegative has all this electron density being pulled towards the O. So a carbon is able to come in with that enzyme and blast into that carbon and create a new bond. And I'm not sure which one it is here because I didn't fully draw this out. But see here, it's like we teach glycolysis. Next drawing here, fats. Fats get long carbon chains, right? Well, here's the kite. You got all these carbons hanging down. Carbon's a diamond, right? So 1H, 2H, 3H's, that shows the methyl part. And then the carbon's coming down. Diamond with the 2 H's, there'll be CH2 groups. But then when you get a double bond here, you get 1H. So 1H, 1H, and then come down CH2. There's another double bond. CH2, CH2. When they're all CH2s, that's when you get a saturated fat. This, with those double bonds,